Centripetal Force Part 2. Okay, so what we're looking at right now is centripetal force, which is what we've seen previously as being like you're going in circles or you're making a turn, right? You're in a car, you're turning left, you're turning right. And what we've done thus far has been horizontal circles. So you're like on a flat plane. What we're going to do now is a vertical circle, something like a loop-to-loop on a roller coaster, okay? So, you're like coming down a hill and woo, and then you fly off into the distance. That's what we're going to be talking about right now. And we're going to obey all of the same ideas that we've been obeying throughout this unit. F equals ma, so a sum of forces equals a mass multiplied by an acceleration. And for centripetal forces, we can say that sum of the forces, or the centripetal forces that we have, are equal to a mass times a centripetal acceleration, remembering that the sum of forces will just be the centripetal, things that are causing the circle to happen, and that our centripetal acceleration, AC, is equal to a velocity squared divided by r, or rather, a speed squared divided by r, okay? Whenever we have objects moving in vertical circles, though, we have to be a little bit careful. We no longer have one force acting on the object to cause a centripetal motion. In our last problems, we had a car making a turn around a bend, and only friction was, allowing that car to turn. That was one force as a centripetal force. This time, though, we're going to have multiple forces acting on our object. And if we take a look at the foxtail, just like we looked at last time. So we take a look at the foxtail here. If I'm spinning it around like this, you might notice that when it's at the bottom, there's like a little bit more of a pull on the foxtail. And if you have like a lanyard or something like that, you just kind of spin it around. You'll notice at the bottom, it's got more of a pull. And you'll notice at the top, it kind of lightens a little bit. And if you really slow down the rotation, sometimes at the top, it kind of just loses it. It doesn't make it all the way around the circle. It just, almost gets there and then falls. And that's because there's two forces at play here. Our two forces at play are going to be the weight of the object and then some sort of pulling secondary force there. Something like a tension or even a normal force if you're sitting in a seat and something's pushing up on you. So if we take a look at, a circle we have here, and let's draw two of these, make life a little bit nicer. If we're going around in a circle, if we are at the bottom of a curve, there are actually two forces acting on us here. There is a weight pulling us down or towards the center of the earth, and we know weight equals mg, but something is keeping us in this circle. If we're going in a loop-to-loop, right? If we're like going around like this, something has to be causing that. And this will actually be the normal force. Something is pushing up on us. If we think about a roller coaster, you're sitting on a seat, and that seat is pushing up on you. That is the normal force that is acting there. So we have two forces in this case. Likewise, if we're at like the top of the loop, and let's say we're going through a loop-to-loop on a roller coaster, so we're on the inside of the track, we have a weight pulling us down here, and our normal force, the seat's pushing on our butt, that is also pointing down. So we've got a scenario like that. If, for whatever reason, we're driving a car and we're going like over a hill, so our car is on the top side of this hill now, well, the weight is still acting down or inward, but the normal force is pushing away from the hill. So we've got these different scenarios of what's going on, and we need to think about what's kind of happening here with our normal force and our weight, because as it will turn out, our centripetal force is really a combination of both of these forces. It's multiple forces added together to give us a centripetal force. It's like a net force there, just like we've been doing. Now, one of the kind of weirder things is whenever we normally talk about forces, we think about a positive and negative direction. And we say, like, let's make the right positive and the left negative, or up positive and down negative. We make that decision. how would you make that positive or negative decision with circular forces? Because I can't say like left is positive because like, right here, this is left, but it's also right at the bottom. And here it's up, but here it's down. So, and that's all going in this counterclockwise direction. So how do we actually choose positive and negatives for our centripetal forces? What we are going to do is we are going to say that anytime a force is acting towards the center of the circle, the center of the arc, those are positive forces. Anytime a force is acting outside of the circle, it's pointing away from the center, we are going to call these negative forces. Okay, so that's how we're going to set up our positive and negatives. And once we do that, it's just an F equals ma, where the a is switched to a v squared over r. And that's all that's going to happen here. So let's take a look at how we can use our centripetal force equation, which we've used previously, and we have, and how we can use it for multiple forces acting in or out of the circle. Now, for our little example we have here, and if you live in the region, if you're one of my students watching this, if you think about the Chick-fil-A, okay, and if you've been driving or driving with a friend, if you know where the Chick-fil-A is at, there's like a kind of bumpy road that goes past the Chick-fil-A. And if you give your car a little bit of gas because, I don't know, you really want some Chick-fil-A for some reason, which, by the way, I don't like Chick-fil-A. But if you're boogieing on this road, you might find a situation where you all of a sudden, like, you dip down, and when you go back up, you're like, oh, it feels like your stomach is coming like up out of your body a little bit. You feel like a little bit lighter. You kind of get that like adrenaline going through you. The reason why that happens is because when we're going over these crests, the normal force pushing on us is changing. And remember, that normal force pushing on us, that is our apparent weight. That is what we feel as humans is like how heavy we are. If for some reason our normal force goes down to 0, nothing is pushing back on us, then it will feel like we're in free fall. So if I kick you out of an airplane, all of a sudden there's no normal force, you feel like you're in free fall, you start panicking a little bit. So when that normal force decreases, as you kind of like crest these hills, you feel a little lighter, you kind of get a little excited, and it kind of feels like you're flying a little bit, okay? So in our problem here, what we have is we're driving along the country road, and we're at a constant speed of 17 meters per second. So that's v, our speed. And in this case, we happen to actually hit a dip in the road. So instead of feeling lighter, you might notice that when you go down a dip, you kind of get pushed into your seat a little bit, okay? And we feel a little bit heavier. That normal force is what we feel, so we feel a little bit heavier. So the dip in the road, that's a average dip. There's a better one. It's approximated as a circular arc, just like I've drawn here. And the radius of this arc, r, equals 65 meters. There we have it right there. What we would like to know is what is the apparent weight, so the normal force, if we have an object ourselves of a mass of 80 kilograms, which gives us a weight of 784, because weight equals m times g, okay? When our car is at the bottom of the dip. So if we just go and set this up, we know the two forces acting on our car. There is some weight here, which equals mg, which equals 784 newtons, and we have a normal force acting on us, pushing us back up. So let's actually solve this first just with variables. Let's not use a single number in setting up this problem and see what we get here. Well, if we do this, knowing that we like to set up the center of the circle being positive and the outside being negative, our F equals ma equation, so the sum of the forces equals ma, and in this case, that's going to equal the centripetal forces equals the mass times the centripetal acceleration. That's going to equal a positive normal force plus a negative weight, so minus weight, equals ma. And in our case here, we want to be a little bit careful because while we will have normal minus mg, this acceleration here is a centripetal acceleration. So this is actually mv squared over r. If we play a little bit of algebra here, we can take this minus mg and add it to the other side. So we simply add that over. And what we find is that the normal force here is equal to mass times the quantity of gravity plus v squared over r. What I did here is I recognized that both of these terms had masses in it, so I just pulled a mass out of the equation. So this is what we will have as our answer. The normal force is going to equal your mass times gravity plus the v squared over r, that centripetal acceleration term. And this is nice because gravity is an acceleration and this v squared over r is also an acceleration, so we can add them together. And what this really shows us is that when we're at the bottom of a dip, we will always feel a little bit heavier. We're always going to feel heavier than gravity because we're like artificially increasing the gravity that we're feeling. Really, it's a centripetal force here. It's the normal force you feel. But we are adding these accelerations together. We feel a little bit heavier. And if we actually wanted to get a number for this, we could do that. We could say normal equals, or the apparent weight equals, the apparent force equals our mass, 80 kilograms, times gravity is 9.8, plus our velocity is 17, which we square, divided by the radius of 65. And when we put all these values together, if we bust out our calculadoro here, we do 17 squared, get a huge number, 289, divided by 65, get 4.44, plus 9.8, get 14.25 times 80. We get, and let's just round this up, we get about 1140 newtons. So 1,140 newtons is our apparent weight. This is more than the 784 we actually weigh. And if that makes it feel like we're getting crushed down a little bit, we feel a little bit heavier than normal. So it all comes from this equation here in black, which allows us to get our final answer here in red. Now, if this dip changed a little bit, if you had a different scenario, if you had a scenario where you're going over the top, how would things change here? Well, if you're going over the top, you're going over the hill, you're feeling a little lighter, you still have a normal force pushing on you, and you still have a weight pulling you down, which means that this equation is actually very similar, but it just it changed slightly. Now, instead of saying normal minus weight equals ma, it will just be weight minus normal, because the normal now just became negative, equals ma for the centripetal acceleration. And if you move some things around here, we move the normal over, we move the ma term over, and then kind of pull out the mass again. What we find is that the normal force will equal the mass times gravity minus v squared over r. And what this shows us right here in this equation, if we're going like over a hill in this setup, is that if we are going over the hill, if you're going fast enough, if you have a fast enough velocity, you could actually get this term here, g minus v squared over r, to equal 0. And that means your normal force will equal 0. It'll feel like you're weightless for just an instant. And if you go any faster than that, your normal force will actually be greater than your weight. And that means you'll go airborne. And this is a really cool thing they do in movies. They run these calculations. If you've ever seen a movie where, a car kind of comes over the hill and it gets a little bit of air. I know in one of the James Bond movies, I think Casino Royale, there's a car chase scene, and he takes his very expensive car and, it kind of like crests a hillside, and then, spoiler alert, he gets into a bad crash, but it goes airborne a little bit. It's due to the fact that the velocity is so high. So in movie production firms, they'll run these calculations ahead of time. They'll tell their drivers, you need to hit this speed at this launch angle coming over the curve, and that'll cause this effect to happen. So pretty cool things between these two equations. These are the equations that we're going to need for vertical loops, talking about centripetal forces here. And we're going to be actually looking at a scenario like this coming up in our next video for our kind of practice problems. But until then, this is finished. Adios, and take it easy.